We finished off talking about how to calculate the future value when you know the present value. Now I want to switch gears and keep talking about future value, but in the context of what's known as an annuity. And really what we're getting at is what is the future value of a number of payments to be made at the end of each year for a given number of years. So for instance, it's often the case that when people win lawsuits, rather than get a lump sum payment, they turn that into annuity where the payment from the person they've sued is put into an investment account and they draw down that investment account over the course of a number of years to try to smooth out their ability to consume from that settlement. Now, let's take an example to illustrate this. Suppose $1,000 is deposited at the end of each year in a savings account, and that savings account pays 8% interest. What you'd like to know is what's the future value of this investment at the end of the 3 years. Important in this example is that the $1,000 is being deposited at the end of each year. In class on Friday, I'll talk about why that matters and how we can make adjustments to our calculations to reflect whether or not that deposit is made at the beginning or at the end of each year. Now, to illustrate this, I've developed a table that looks something like this. You'll find it in your notes on page 4 near the top. And so what I've done is I've listed the 3 different years. We've got a column indicating the deposit that happens in each year, a column where we're going to calculate the compound factor, and then where we're going to calculate the future value of that 3 years hence. So to begin with, recognize that you're going to deposit that $1,000 into your savings account at the end of year 1. And so what that means is that you're going to earn interest on that $1,000 in year 2 and year 3. Now, important in this is that the interest in year 3 is also going to be compounded interest because you're going to get interest on the interest that you earned in year 2. So because of that, we actually calculate our compounding factor as 1.08 raised to the power 2. So all this is saying is that with an 8% interest rate and the fact that my money is going to be earning interest for 2 years, then the compound factor is 1.1664. Now I know that I have to put the power 2 outside of the bracket because the deposit happens at the end of year 1, and so I'm only earning interest in year 2 and year 3, that is for 2 years. Once I have my compound factor, I simply multiply it by the deposit, and that gives me the future value of that $1,000 that's deposited at the end of year 1, but at the end of year 3. So after 2 years, that $1,000 deposited at the end of year 1 is worth $1,166.40. Now, by the same logic, the $1,000 that's deposited at the end of year 2 is going to earn interest in year 3 and is going to earn 8% interest in year 3. Because of that, the compound factor is simply 1.08. We don't actually have any compounding that's happening because we're only earning interest in that last year, year 3. When I calculate the future value in year 3 of that $1,000 deposited at the end of year 2, it ends up being $1,080. Now lastly, at the end of year 3, you're going to deposit $1,000 as well. But remember that we want to know the future value at the end of year 3 when you've deposited that last $1,000. Because that deposit happens at the end of the time period that you're interested in, there's no compounding factor to be calculated. That's because you're not earning any interest on that $1,000 that you deposited at the end of year 3. So the future value in year 3 is simply $1,000. If we add those 3 up, what we find is that the future value in year 3 of those 3 annuities, those are payments into your savings account, are $3,246.41. We'll go through another example of this in lecture on Friday to illustrate how it's used. Now, one thing to emphasize is that we can break the amount of money up into 2 different components at the end of the day. So you've invested $3,000 and you earn a total interest of $246.40. Now, the calculations that we've also gone through are a bit laborious, and in fact, they're kind of simple-minded calculations where it can sometimes be easy to make simple mistakes. To make it a little easier, we actually have a formula that can be used to calculate the future value of an annuity. That's shown in the second to last line on this slide. And it says the future value equals the payment, that's the annuity, times 1 plus the interest rate, all raised to the power n, minus 1, all divided by I. Now, as I indicated in the video previous to this, I will give you the equations on the midterm exam and the final exam, but I won't tell you what they are. You'll have to remember what they are and how they're to be used. I provide them simply to make sure that you're plugging the right number into the right spot. Now, another way you can calculate these kinds of future values of an annuity is to use the tabulated values of those compound factors. As I indicated before, most calculators actually do this for you very simply, and so a lot of these tabulated values don't actually get reported anymore. Now, we've been talking about trying to find the future value when you know the present value, and that involves compounding. Another approach that gets used in dealing with the time value of money is finding present values. So for instance, maybe you know the future value of something and you want to know its worth today as opposed to in the future. When we're doing this, we do what's called discounting. This is simply the procedure for finding the present value of an amount of money when its future value is known. It's really the opposite of compounding if you want to think about it that way. So for example, think about the very first savings example that we talked about. The present value of that $1,259.71 to be received at the end of year 3, assuming an 8% interest rate, is simply $1,000. We can go back and forth between these two things interchangeably. Now, to give a little more sense to this, let's actually think about what we're talking about. So what I've done here is I've plotted time on the x-axis and dollar amount on the y-axis. And if we think about the present value of $1,000 today, if we had compounded interest of 8% for 3 years, that would give us a future value of $1,259.71. I could then compare that future value to some other investment alternative 3 years hence that's been calculated in the same kind of manner to see which one would actually be preferred in 3 years in the future. Alternatively, if I knew the future value, I could discount that back to the present value and compare it to some other alternative whose present value I already know. So what I want you to remember is that when we're thinking about the relationship between time and money, we generally think that that relationship is increasing. That is, as time increases, the dollar value goes up. And as we go forward in time in our analysis, moving from the present value to the future value, that involves compounding. When we go from future values to present values, that involves discounting. So we're just undoing what we might have done in calculating a future value. The equation to find the present value of a single payment to be received in the future is actually quite simple. In fact, if we take the future value equation and we divide both sides by 1 plus I to the power n, we get the present value equation shown in this slide. So what it says is if I want to know the present value of something, some payment to be received in the future, and it is a single payment to be received in the future, all I need to know is its future value, the interest rate, and the number of time periods. If I have that, I'm done. It's just that simple. So let's illustrate this with an example. You might think about planting Christmas trees. A lot of people actually do this. It tends to be a seasonal activity, but it also tends to be a fairly lucrative activity. And so you might wonder, what is the present value of a crop of Christmas trees that will be ready for market in 8 years at a value of $10,000? And so the idea here is that when you plant the seedlings, they're not going to be ready for harvest this year. They're going to be ready for harvest sometime in the future. And you may know the price at which you'd like to sell them at some point in the future and calculate the value of that tree crop 8 years from now to be $10,000. Well, you're not necessarily concerned about its worth 8 years from now. What you might be concerned about is what would that be worth in today's dollars. And so let's assume an interest rate of 10%. And let's suppose that those trees, beg your pardon, cost you $5,000 today to plant. What you'd like to know is whether or not the present value of the revenue from the sale of those trees in 8 years is less than or greater than the cost to plant those trees, because that will give you some indication of profitability. So all I'm going to do at this point is then substitute in the future value, the interest rate, and the number of years into the present value formula. That's what I've done here. So make sure to note that we're expressing the interest rate as a decimal. Now, if I calculate the value of the compound factor, you can also express it multiplicatively, and that's what I've done here. So 1 over 1.1 raised to the power 8 is simply 0.4665. And so I'm multiplying $10,000 by 0.4665 to determine the present value. And what this tells me is that the present value of that $10,000 in tree revenue 8 years from now is worth $4,665 today. Since the trees are going to cost me $5,000 to plant today, what this means is I actually don't want to undertake this investment because my revenue stated in today's dollars is less than the cost in today's dollars, and it doesn't make sense to undertake this as an economic opportunity. I'm going to lose money. We can also calculate the present value of an annuity. And the way to think about this is that you might receive an annuity from a bank or from a relative or from some sort of legal settlement, as I indicated earlier, and that gives you a payment at different points in time. So for instance, if you had 3 payments throughout time, what you might be concerned with is not necessarily how much it is at any individual point in time, but its present value. That is, what are those annuities worth to you today? And so let's illustrate this with an example, because the calculation is relatively straightforward. So suppose an annuity of $1,000 will be received at the end of each year for 3 years, and that the interest rate is 8%. What you'd like to know is the present value of that income stream, or that annuity. This table will help illustrate the concept. I've got the different years on the rows, and then I've got a column for the amount that you're going to receive at the end of each year, the present value factor, and then also the dollar value stated in present value terms. You're going to receive $1,000 at the end of year 1, and so you want to discount that back to the start of year 1. And to do that, you divide it by 1 plus I to the power n, where in this case, n is simply going to be equal to 1, and that's because you want to discount it to the start of the first year when you receive the money at the end of the first year. If you make the appropriate substitutions and calculate through, that present value factor is 0.926. To get the dollar value in present value terms, I simply multiply the amount that I'd receive at the end of year 1 times the present value factor, and I'd get $926. Now, in the end of year 2, I'm going to get $1,000 as well, and so what I want to do is discount that back from the end of year 2 to the start of year 1. And so I would divide that $1,000 by 1 plus I to the power n, where I is the interest rate, and in this case, n is equal to 2. That's because I'm discounting it back 2 years, from the end of year 2 to the start of year 1. And if you make the appropriate substitutions and calculate what the present value factor is, you'll see it's 0.857. And as before, I simply multiply the dollar amount by the present value factor to get the present value, or the dollar amount in present value terms, so $856. And then lastly, we're going to receive $1,000 at the end of year 3. What we need to do is discount that back to the start of year 1, and we'd again apply the present value factor like we had done in the 2 previous years, only now n is going to be equal to 3, and that's because I have to discount that $1,000 I've received at the end of year 3 back 3 years. And when I do that calculation, it is 0.794. And so the dollar value amount in present value terms is $794. What I would then do is I would total up the present value of those dollar amounts from each year and find that that annuity in present value terms is worth $2,577. Now, that's a lot of calculations and a lot of busy work, and in fact, it's fairly easy to make calculation errors in that kind of a setup. And so we actually have an equation that makes it a lot easier. That's the middle equation shown on this slide, and it says that the present value of an annuity is equal to the payment in that annuity times 1 minus 1 plus I to the negative n, where n is the number of time periods, all divided by I. So it looks kind of complicated, but if we actually think about what gets substituted where, we end up with the same result. So on the bottom line, we've substituted $1,000 for the payment. That's the annuity that we're going to get in every year. I've substituted in 0.08 for I, the interest rate, and n is simply equal to 3, and that's because I'm discounting it back from the end of year 3. And if you calculate the present value of the annuity with this formula, what you find is that it's exactly equal to what we calculated through the manual approach taken previously. My encouragement to you would be to think about using these present value and future value of annuity equations wherever you can. It makes the calculations much easier, and you're much less apt to make a silly math mistake in a calculation that could cause problems later on. Now, the point of all of this is actually to get at investment analysis and to prime you guys to be thinking about investment analysis. And so we're going to shift gears a little bit now and think about how we would go about determining the profitability of an investment or comparing the profitability of two or more alternative investments. Now, this is important because it's often the case that when you're going to invest money, you've got choices. And those choices have to be guided with some sort of rhyme or reason. To just sort of select one investment alternative in a willy-nilly way could create great opportunity costs and could create irreversible investments that cause problems for you either financially or in terms of the operation of a business. So it's important that you understand how to actually compare different types of investments when faced with choices. There's really two broad issues that are associated with investment decisions. The first is very simple. What's the return? What's the percent return that you could earn from that investment? And can you actually rank investment alternatives based on the returns? The second is whether or not the investment is feasible from a cash flow sense. It's sometimes the case that the returns to an investment might be very good, but the cash flow needed to actually pay for that investment isn't necessarily available, and so you might not be able to afford to undertake that investment. A good analogy about this actually is one my father taught me early in life, and that's you don't want to be house rich and cash poor. And the idea there is don't buy beyond your means. Don't buy a house that has got potential for a significant increase in its value over the course of its life, but leaves you struggling to make the mortgage payments because not being able to cash flow the mortgage payment has certainly some undesirable outcomes with respect to things like foreclosure. Now, what's important to remember is that an investment can generate good returns over time, but it might be infeasible in the cash flow sense. The reverse is also true. Cash flow may not be a problem, but the returns are just so pitifully low that that investment alternative isn't very attractive. And so we often use different ways of comparing investment alternatives to get a sense of what do the returns look like and is the cash flow for this investment such that I can afford it. To do this, we need different pieces of information. And there's usually 4 pieces of information that you need for a thorough analysis of an investment. You need to know the annual net revenues from the investment. That is, what is it going to give you? What are you going to earn from that investment over time? Its initial cost, or the outlay that you have to pay. You sometimes also need to know what's called the terminal or salvage value of the investment. And recall, we talked about salvage value when we talked about capital goods. This is simply the value of that investment if you go to sell it after you're done. Think about the value of a used car when you're done with it. That could be thought of as a salvage value. The other thing that you're going to need to know is the interest rate or the discount rate that's going to be used to actually undertake discounting when you're evaluating these different investment alternatives. Now, we're going to illustrate investment analysis during the lectures using data from table 5.1 from the notes. I'm not going to get into the details during the video, but we will get into the details during the lecture. What we're going to do is use that information to illustrate 4 different types of methods to compare investments. These 4 different methods are the payback period, a simple rate of return, the net present value, and the internal rate of return. This is actually a really good place to stop, and so we'll pick up with a discussion of what the payback period is in our next video. See you in class.